Good morning, everybody. Welcome to Nine Seminars again. LeTourneau University, brought to you by the Department of Chemistry and Physics. Yes, today it's an exciting day. We have people coming back to us to visit. Yes, at least one of them is coming back to visit. All the other ones are new to LeTourneau, so you'll get a chance to meet them. Okay, so Sarah Schlimme is with us today. She graduated from LeTourneau with a biomedical engineering degree back in 2023. And now she's working on a master's in prosthetics and orthotics. Is how we say that? Okay. And they're going to talk about feet. So, watch your feet today. Got good clean ones because they may be coming around taking over here. Right? And we use that in the Gen Chem lab. Make sure you're not wearing flip flops and stuff. But here they have other materials here. So Sarah's going to introduce the rest of her team for us because I don't know who they are, but she does. And so she'll tell you that. And then after the seminar, we get out at 11:50. Okay, we'll have a little break and then we'll go to lunch. Yes. So if you're interested in what life is like in graduate school, how to get to graduate school, all those kind of things, join us in the Joyce Room or the Corner Cafe. You'll have more chances to talk with Sarah and maybe some of the rest of her team if they can stick around. Okay. All right, let's do a warm welcome for Sarah.
Everyone, thank you so much for coming and to listen about our research that we've been doing. Thank you so much for Dr. DeBoer for inviting me back. We're going to do a little bit of after I introduce the team, we're going to do a little bit of an overview of what our field is, just some definitions and kind of what we do. And then we're going to talk about how engineering plays into our field as well for those who are interested. And then we'll get into our research, which is comparing two types of feet. One is a 3D printed foot, and the other one is just a prosthetic foot that's on the market called a flexible heel foot. And hopefully we'll be able to do some definitions so that this makes more sense by the time we get there. So first, I'm going to introduce my team. As you know, I'm Sarah Schlimme. I got into this field because I had friends who had prosthetics and orthotics, just prosthetics. And I learned more about the field through them and got to experience a little bit what the patient side looks like and what it looks like growing up with prosthetics. And as I was trying to figure out what I wanted to do, I got a shadow at Scottish Rite Hospital in Dallas. And that was so exciting. And I really enjoyed it, fell in love. So here I am doing what I want to do.
My name is Adlai Gomez. I graduated from Brigham Young University, Idaho, with a degree in exercise science in 2022. And I got into this field because I love how the hands-on aspect combines with the clinical thinking, just all in one field. I'm a big fan of it.
I'm Reese Francis. I also graduated with science, bachelor's in science from University of Central Oklahoma. I found my way in the field. I like to tinker with things. I was making dressers at home, putting up all of the mirrors and stuff like that. I also wanted something that involved patient care.
I'm Laura. I got my biomedical engineering degree from Virginia Tech in 2023. I got into the field because I really liked biomechanics and my studied courses and actually creating prototypes. And I also really wanted to have autonomy over the devices that I was making and have direct patient interactions. So I shadowed and fell in love with the field. And so a little bit about us and what we do. We are a full-time post-baccalaureate graduate program. It's a 19-month program in Dallas. We start in May, so I started 2 days after I graduated. And then we graduate this coming December, which is very exciting. We have a well-rounded curriculum that's focused on academics. It's really heavy on the clinical side. We have a ton of patient models, and also we have research experiences, as we'll hear about today. All of our professors are actually current clinicians, so we get a really good, well-rounded, it's focused on current education. It's really awesome. We're also affiliated with Dallas's top hospitals. So if you are interested in learning more about our program, we'd love to answer questions. But these are some of the devices that we get to work on. These are 40 of my closest friends. We're a pretty small cohort, so it's a pretty small field. But we all get really close and get to make a bunch of people.
A little bit of background into what the field is, the field of prosthetics and orthotics. So here we have Amy Purdy. I don't know, you may or may not have seen her. She's a Paralympian snowboarder, was also on Dancing with the Stars. Pretty cool, pretty famous. But a little bit into what this field is and what it means to be in prosthetics and orthotics. So we go to school to become, and we learn to be prosthetists and orthotists. So we learn both and we go to school for both. Eventually you can choose to practice one or the other or both. But to see what a prosthetist is a healthcare professional who fabricates, evaluates, and fits patients with custom-made artificial limbs called prostheses. That's a fun little fact, right? The actual device is not a prosthetic, it's a prosthesis. So write that down, there'll be a quiz later. Right. So anyway, a prosthetist replaces a missing limb for patients with limb deficiency. So you could have a limb deficiency later in life through a traumatic accident, or you could have been born that way through congenital difference. Either way, we can help you out in the field of prosthetics. On the other side, an orthotist is a healthcare professional who designs, fabricates, and evaluates and fits custom-made orthopedic devices called orthoses. And an orthotist controls an existing limb or joint that needs extra structural support or help with the movement. So here on this next slide, we're gonna see a little bit about where you may have seen the field of prosthetics and orthotics in action. We have the fabulous Regina George, as we all know, have seen. She's wearing a halo, which is an orthotic device that is used to help people with a cervical fracture. Here we have Ezra French. Ezra French just recently participated in the Paris Paralympics, and he's an above-knee amputee. And his events were the 100-meter sprint and the long jump. So if you were watching the Paralympics, probably saw him. And then, does anybody know where this scene came from? Oh my God. So Forrest Gump over here is running out of his braces in this scene, right? These braces are what's called a K-foot. They are a knee, ankle, foot orthosis. So we make these as well.
So part of our job is to pick components that go into a device called a prosthesis. And some of those components are socket design. So that is, we get to choose the shape of the socket and basically what kind of fit we want for our patient to have. And that's the part that you see that goes on the leg. And then the suspension system is what holds the piece onto the limb itself. So you can use suction, you can use pin and lock, or just make it anatomical. So that means that if their bone has a shape that allows the prosthesis to kind of grab around the bone and hold onto it, that's another good way to suspend prosthesis. And then the interface is another thing we have to choose, and that's can be no interface, so just skin against the socket, or socks or gel liners. Gel liners is probably the most common. You can have a pin or a suction system. And then joints are really important part of gait mechanics, and so it's really important to choose one that is good for your patient. These are important to choose for patient safety and their activities, but they can be mechanical, hydraulic, pneumatic, or microprocessor. So they can be powered by electronics. And these are hip, knee joints, and ankle joints. However, the ankle joint is usually incorporated into the foot. So that is kind of the next main component that we're going to choose is the prosthetic foot that you're going to use. And that's determined by a patient's activity level, which Reese is going to go through in a little bit. And that's what our research is focused on. So that part is really important for the patient to be able to accomplish the goals that they want throughout the day. And then adapters and accessories, anything that's going to enhance the patient's experience with the prosthesis or add extra function or safety to the prosthetic. So the gait cycle is something that if you've taken biomechanics, you've learned about this. Hopefully it's been drilled into you. It definitely was drilled into me both in undergrad and grad school. It's really important. But there's two phases, the stance phase and the swing phase. The stance phase is when the foot is on the ground. So first contact to the ground, then it leaves the ground, and then swing phase is when the foot swings through to the next step. Our focus is going to be on the mid stance to terminal stance because we only care about what's happening at the forefoot because we're testing forefoot stiffness of these feet. So that mid stance is when the foot is in the middle of the stance, most of your weight is on that leg. And then to terminal stance, if you've been pre-swing, it's the last part of the toe touches the ground. So your gait is, the goal of your gait is to move forward in a straight line. And your body also moves a little bit side to side and it moves vertically up and down to the center of mass. So it's really important to have efficient gait mechanics because you don't want to get really exhausted with inefficient gait up and down, side to side a lot. And so with prosthetics and orthotics, specifically prosthetics, as patients lose joints, so they might lose some toes, and they might lose their ankle, they might lose their knee. The amount of energy they need to walk increases no matter how good their prosthetic is. And so it's really important as we choose these components, as we choose feet, that we're going to give our patients an efficient gait. Specifically for our research, since we're talking about feet, ankle motion during the stance phase helps with shock absorption and also smooths that up and down motion. So those are the things that we want to look for in prosthetic feet.
So Sarah briefly mentioned activity level and what that means. So we determine activity level based on their K level. So it's K0 to K4. And based on that, we can pick components for that specific activity in that patient. So basically, I'm just going to talk about each section of the K levels and then what foot would be indicated for them. So with our K0s, these are individuals that are just transferring, they're not necessarily ambulating, so a prosthesis wouldn't be helpful with their mobility or improve their quality of life, so they would be indicated for one. But our K1s, they're household ambulators, so they're doing transfers with these, and when I say transfers, I just mean from like a chair to another chair, a chair to the car, things like that. So they would be doing transfers or just ambulating on level surfaces at a fixed cadence, just like one speed. And they would be indicated for a satch foot. So a satch foot stands for solid ankle cushioned heel, and it has a rigid heel, which is the toe portion of the foot. And that helps with pushing them off in stance to be able to provide some momentum into their next step. So our K2 is also a community ambulator. They can walk over curbs, stairs, and things like that. Also at a same cadence with a flexible heel foot, sorry. And that's what they're indicated for. And that's also what we'll be talking about in research. Our K3 foot is community ambulators. They traverse over environmental barriers and they also engage in other activities outside of ambulating, so like exercises and things like that. And they would be indicated for a dynamic response foot, and that's carbon fiber. So when they're walking, they're getting energy return with their mobility. And our K4s are very active patients. These are children, active adults, athletes, and they will be able to withstand high impact activities with this dynamic response foot.
So now we're going to talk about the role of engineering in prosthetics and orthotics. So this is just some exciting, cool things that happen in our field. Some recent advancements we've had is the socketless socket, which is the spinning thing here. This is for someone who doesn't have their knee, so it's called an above knee amputation socket. And this is designed to eliminate that need for the traditional socket, which is a little heavier and thicker. And so it's supposed to provide a lighter weight, more adjustable socket for patients. And then we have the C-brace and C-leg, which is a microprocessor component on a brace. And for a prosthetic, the C-leg, it is a microprocessor knee component. And this allows patients to be able to walk on uneven ground. It adjusts to the patient's needs, as well as for C-brace, it can help patients who have no quad strength be able to stand. And then myoelectric technology is what you've probably all seen when you hear prosthetics. You think of like prosthetic hands and all those cool moving things. And so that technology is powered through the human muscles that they still have left, and then they can power the hand to move for them. Bone anchor is recently kind of growing in our field, but it was FDA approved for above knee patients. That picture is an above knee patient in 2015, and this basically eliminates the need for a socket. There's still a huge need for sockets. This doesn't for everybody, actually most of our patient population. Right now, this is still a pretty experimental for some of them. So, but that's really exciting advancement, gets rid of the need for a socket. And then additive manufacturing and computer aided design, which is 3D printing and CAD. So we're going to get into that a little bit.
So 3D printing is transforming how we're making devices in the field right now. It's very big. So it will allow us to produce consistent, repeatable devices, cut down on production time, allow quicker deliveries to patients, reduce waste by using only the required materials needed to print, use less expensive materials compared to traditional methods. We are finding challenges within 3D printing as with incorporating something new into any field. Some of those challenges include just like a learning curve, basically, figuring out how to do it. There's always trial and error with everything. And also the upfront cost of a 3D printer, depending on how high quality it is. Also, any adjustments and errors when we're using different settings and infill percentages and things like that, which we will get into. 3D printing applications in prosthetics and orthotics include thus far doing custom prosthetic covers, 3D printed test sockets, and bone covers, and then spinal and cranial orthoses. So R&D in the field, we're continually innovating in the field through different companies that are listed up here. I'm just going to list a few of their achievements and what they're most notably known for. So OSER does an iLim. It's a bioelectric prosthetic hand with psi articulating components. Autobach is a global leader in both prosthetics and orthotics, focusing on mobility solutions. Bowerfield AG, it specializes in rehabilitation and sports medicine. Willowwood does gel liners, an interface that's in a socket that Sarah mentioned. Blatchford, and also including Martin Bionics and Coapt, which does pattern recognition, and then Martin Bionics with the adjustable socket.
All right, so now getting into a little bit more about the focus of our research, what we're looking at here. So this is Taiwo Akinsanya. He's a prosthetist and orthotist in Lagos, Nigeria. And so in his practice, he found that mainstream components were great, but they were costly. And so overseeing products that were alternatives, he would have them ship over. They would take a long time to ship, and they were cheaper, but they just wouldn't last as long. So he wanted to find a solution where he could be able to get the components that he needed. They would last the adequate amount of time, and they would work for his patients. So in order to solve this problem, he created the Macy foot. And the Macy foot is a 3D printable foot. Here we have some examples that we're going to pass around here. These are you can test them, bend them. They're like $2,000, so don't break them. Just kidding, they're not really $2,000, but please don't break our piece. But anyway, so he invented, this is his design, right? Is the Macy foot. So he wanted to create something that has a flexible metatarsal system, which is kind of this 4-foot part right here. So you're going to be able to see it when it goes around. That part has bridges, so it can compress, it can bend, that mimic somewhat a regular foot. It also has a curved heel and a compressible heel as well. You'll see in another picture until you get that feet, kind of what that looks like. And so what these are is, because they're 3D printed, they can be customizable in sizes from pediatric all the way up to adult, customizable in size, waterproof, and they've been recently made available to prosthetic and orthotic innovators in Pakistan as well. So the growth there, we're growing there, we're getting a little bit of better foothold. So as Reese had explained, in the flexible keel, right? Flexible keel is for that limited community ambulator, right? So somebody that can go inside and outside the house, but they're not walking very long distances. So that's what this type of foot is designed for. And Taiwo, the creator of this 3D printed foot, the Macy foot, most compares this design the flexible keel foot to his design of the Macy foot. So that's why we're comparing these two in our research together, because that's also what he suggested. And they both have one kind of common contributor of them is that they both have very limited or no moving parts. The Macy foot has no moving parts, and most flexible keels do not have any moving parts as well. And so this internal keel that is inside this foot, it's just kind of a carbon fiber part of the foot that is able to bend and it's able to be flexible and adapt over to the surfaces it's stepping on and produces easier rollover. So when you're walking.
So all probably know there's multiple types of 3D printing, but just to give you guys a brief overview, SLA printing uses liquid resin to cure, or uses a laser to cure liquid resin layer by layer to make a material. Formlabs 3D printing uses this type of methodology, if you guys are aware of that. Then there's selective laser sintering and multi-jet fusion. Those are pretty similar. Both use nylon-based powders that are then cured into a hard shape. One is cured by a laser for the selective laser sintering, and the other one is infrared light for the multi-jet fusion. But those are fairly expensive, so they're not really that common. And probably what you guys are most used to is the fused deposition modeling, FDM printing. That just extrudes your filament layer by layer. I kind of think of it almost like a hot glue gun that's really controlled. But that's the cheapest form of 3D printing and also the most readily available. So this is the 3D printing that we used for our research. The filament that we used was TPU, which stands for thermoplastic polyurethane. Thermoplastic polyurethane is a copolymer made up of alternating hard and soft sequences. Those hard and soft segments can then be manipulated to control the material properties. So material property scientists and engineers can then manipulate that to get the exact material properties that you want. So for example, if you wanted your TPU to be more flexible, you could incorporate more soft segments to your TPU. But if you wanted it to be more durable, you could incorporate more of those hard sequences or segments. But the basic material properties for TPUs include flexibility, durability, shock and impact resistance, and vibration dampening. These material properties can be really helpful for prosthetic applications, especially for feet, because you can really target what aspects of the gait cycle that you want to target with this foot. So, for example, that shock and impact resistance and that vibration dampening can be really helpful at initial contact when you're placing all of your weight onto your foot. There's also this thing called a shore hardness scale. Shore hardness scales are used to classify the hardness of TPUs and other objects. It's a measurement of a material's resistance to indentation, which can kind of directly relate to how stiff or hard a material will be. So we utilized a TPU filament with a shore hardness scale of 95A. That like roughly equates to like a shopping cart wheel. Yes. So throughout our literature review, when we were first getting into this project, we found that a lot of the studies cited the ISO standard for structural testing of lower limb prostheses. This standard gave guidelines for structural testing of all lower limb prostheses, either as entire units or as separate components. We were most interested in the parts of that focused on the separate prosthetic foot. So this standard gave instructions for how to set up testing for determining proof strength, ultimate strength, and fatigue strength. We were most interested in proof strength and ultimate strength. So proof strength is defined as the static load representing an occasional severe event which can be sustained by the prosthetic structure and still allow it to function as intended. Ultimate strength is very similar, except that the load would damage the prosthetic foot and render it unusable. So that's like getting into your elastic versus plastic definitions. So this testing setup included loading the component with predetermined forces, then documenting the deformation that it sustained or displacement that it sustained, which could then be used to calculate stiffness, because stiffness is just defined as an object's ability to resist deformation when a force is applied. We also learned that you can angle the prosthetic foot to isolate the forefoot and hindfoot components, which are 20 degrees of dorsiflexion and 15 degrees of plantar flexion respectively. So this bottom right image shows how you would do that for isolating the forefoot and hindfoot. So even though we weren't able to have access to a machine that does that, we did try to replicate it as best we could with the resources that we had. So we couldn't exactly replicate the ISO standards, but we did take a lot of inspiration from it to try and get it as close as we could.
So our study aims to quantify the forefoot stiffness of the 3D printed Macy foot compared to that of the College Park principal heel foot. Our independent variables were the 4 different types of feet. So we have 3 3D printed feet with the 1 College Park foot, and infill percentages of 40, 60, and 80% infill. Our dependent variable was measuring stiffness expressed in millimeters degrees. We were maintaining several constants to ensure accuracy. That included using a 24 centimeter foot size, which is the size of foot that's being passed around. Alignment during testing, testing machine and procedures, 3D printing specifications, including the gyroid infill pattern, and using the TPU filament and the bamboo printer. The clinical application goal is to determine which infill percentage of the Macy foot is the most appropriate for prosthetic use. So we're trying to compare, but also determine clinically which one would be as similar to use.
Okay, so the printer we used, as Reese mentioned, is the Bamboo X1 printer. You guys have it here in Maker Lab. I tried to use the one here in the Maker Lab, but could not do my own troubleshooting from Dallas. Couldn't stay here multiple days. So thankfully, I was able to get in contact with Amber Johnson, who's here at LeTourneau, and she helped me print our feet for us using this printer that she has. And it's a good printer that can print high quality prints, and it has the right volume for the print size to be needed, as well as really good print speed. So the settings we used, these were recommended to us by Taewo and his other people that have been doing printing for him and testing. These are kind of the guidelines that we followed based on his recommendations. So we started out with 4 wall loops, and this is basically the perimeter of the printer prints around the print. And then the 8 top and bottom shell layers. These are the amount of layers before it starts printing the infill pattern. And so this is the goal of this was to add more stiffness to the foot while keeping it light. And so that's why these numbers were chosen. And then the gyroid infill pattern was also recommended by Taewo. Just some stuff about it is a complex undulating pattern that is able to have strength and resistance from all directions and is different at every level. You can see there in the pink, that's an example of the gyroid pattern. And then, as Reese mentioned, our dependent variable was the infill density. So we wanted to see what infill density most compared to the Breeze foot, the foot already on the market, at 40%, 60%, and 80%. This gives us flexibility and stiffness, and also like the less infill we have, the lighter weight the foot is. And then our volumetric speed, we kept at 3.2. This gave us a high quality print without clogging. And also, so we also use the bamboo slicer for all of this. As you can see, these are our settings. We just stuck with the standard TPU presets for everything except for what I just talked about that we changed.
Let's take a quick look at a machine that we used. We used something we called the sagittal stiffness machine. And so this machine was used for a previous study that looked at the carbon fiber layup and width for an ankle foot orthosis. So we made modifications to this machine so that it could be used for our purposes. One of the first modifications we did was to raise this base plate right up to the center of rotation of the motor, and then align that with the foot. So we would be able to isolate just the forefoot in our studies. And so we have a lot of other modifications that we did. This is more of our methods. So one thing that we did is we took a pylon, which is basically just a tube, and we had these tube clamps attached to them on the bottom and on the top. And these tube clamps have set screws, which you can manipulate so that you can have it leaning one way or the other way, depending on the type of prostheses that you made and the way the patient stands and walks. It's beneficial to be able to align them a certain direction, a certain way. But in this case, we wanted to use a laser to align them vertically in both the sagittal and the coronal plane. So we did that here. Then after that, we attached a 7/8 pipe, which you can see right there. And then that's what's going to be connected to our machine. So again, that was also aligned vertically in the sagittal and coronal planes using this laser. And then additionally, we see right over here, this is kind of the foot in the base plate. And then there's that tube, the tube clamps, and then the pipe is just right over here. So this is that center rotation that we're talking about. And then just the final adjustment that we made is to outside the foot 5 degrees in external rotation. That's a fun little fact. When we walk, we don't walk completely 0 degrees straight in the direction, but our feet are actually about 5 to 7 degrees externally rotated. So just a little bit out. So in order to mimic that normally, we made that adjustment in our machine as well.
For data collection, the base plate of the testing machine rotates from a neutral position, which is 0 degrees, to 20 degrees of dorsiflexion and then back to that neutral position. And this rotation will occur 5 times at a rate of 15 degrees per second, mimicking normal gait. And the machine captures the base plate position in degrees in the resulting torque and newton meters. And each foot will undergo 7 different trials.
Oh, you can see this is what we're doing. So it'll go 7 times.
Right, so our data collection gave us well over 10,000 data points for the trial, but a significant amount of those points were zeros just left over at the end where the machine was still reading position and force data, but the trial had ended. So we needed to get rid of roughly 4,000 data points of zeros. So in order to efficiently delete those and calculate our stiffness values, I wrote a quick MATLAB script that imported those raw data sets, deleted the excess zeros, calculated the slope and R-squared values. So we had to account for the stiffness of the machine itself as well. So we also ran trials with nothing on the base plate, just to kind of give us a baseline stiffness. So then once we calculated the mean stiffness of the base plate, we subtracted that from the stiffness that we calculated for our feet. Finally, the program displayed the average stiffness for each foot type across all trials, and we created this graph for each individual trial. So we had 7 of these total, which then this slope turned into here. See that? So that way we could compare each slope or each stiffness of the trials for the foot. Okay, getting into our preliminary results and discussion. So this is our 40% infill trial. That's our lightest weight foot. We calculated an average forefoot stiffness of 0.33003 newton meters per degree. You can see there's very low variability in the trials. It's pretty tiny, so you actually can't see that. But the R-squared values, our lowest one was 0.95 and our highest one a little bit more than 9 feet. And we also had pretty low standard deviations, so we're really happy about that. Moving into our 60% infill settings, our average stiffness increased to about 0.4 newton meters per degree. Again, we had those high R-squared values and that low standard deviation. These were our results for the 80% infill settings. We calculated an average forefoot stiffness of 0.36403 newton meters per degree. Again, very low standard deviation and very high R-squared values, although we were surprised at 80% infill trials resulting in an actual lower stiffness than the 60%. So that doesn't make sense. But Reese is going to touch on our thoughts about this later. This is the College Park 3's flexible keel foot that we went through the same testing with. As you can see, that's non-linear. So after about, this 10-degree mark here, you can see it kind of stabilizes in a linear fashion. But all of the values before this 10-degree mark are kind of causing our slope to decrease, which directly equates to our stiffness values. So when we look at this overall combined entire 0 to 20 degrees, we have a pretty low stiffness value that equates pretty similarly to our 40% infill foot. But those two graphs aren't really necessarily comparable because one's nonlinear and the other one is. But that nonlinear trend and then the resulting nonlinear graph is actually what we would expect from normal ambulation, which is what the college part of flexible keel foot is trying to simulate because of this four-keeled shape is what they call it. So going from the forefoot to the heel, it's composed of this composite material structure, and that shape is trying to mimic normal ambulation. So during normal ambulation, the metatarsal phalangeal joint, which is really just like the ball of your foot, actually absorbs energy and increases in stiffness when they're getting dorsiflexed during terminal stances to help you prepare for push-off and propulsion forward during swing phase. So essentially your forefoot during normal ambulation increases its stiffness until it reaches a maximum stiffness for push-off or toe-off, which we found with the college part free foot would sustain after 10 degrees of dorsiflexion. So between the 5 and 10 degree mark, you can see that slope would be constantly changing. So the derivative would be positive, which until it finally reaches this kind of maintained slope after 10 degrees. So here you can see we just decided to crop off that nonlinear portion of the data to isolate where the foot was the stiffest. So that reflected, or at least it would reflect push off or toe off where the foot is trying to be the stiffest it can be. And that increased the total stiffness significantly to 0.46.
So in comparing our results, so in the table here, the 3D printed foot with 60% infill exhibited the highest stiffness among all of the 3D printed feet, demonstrating a comparable performance to the college freeze foot. So not the 80 like we first anticipated, it actually ended up being at 60. It is lighter. Oh, sorry. So the 60% infill also offers practical benefits. It's lighter than the 80% infill and reduces that production cost due to the less material used in printing. Our findings indicate that the infill percentage does not indicate stiffness, as the 60% infill surpassed both the 80 and 40 infill in performance. And we're proposing that the variation in lattice structure in the Macy foot could contribute to that unexpected infill performance, but we are still working on our statistical analysis and figuring out if that is correct. That's just like an inference we're making right now. And then our statistical analysis. So we're currently collaborating with a statistician to conduct our analysis. This is something we're doing right now. So this is just our current plan that we prepared to do. Basically, we're going to do a non-parametric ANOVA. So this is going to select and compare the forefoot stiffness across all 4 groups. This choice was made due to our small sample size of only having 7 data points in the group. And for our analysis, we are setting our significance level to 0.05. And if our Kruskal-Wallis test, which are non-parametric ANOVA, that indicates a significant difference among the groups, we will perform a pairwise comparison. And that would be with our 60% comparing with our freeze foot. So we would be able to apply that bond theory correction as well. And that is just to indicate differences between those feet. And then we are going to conduct using the SPSS, which is just a statistical analysis testing data. And so that is going to be to ensure accurate analysis or relatable comparison of the forefoot stiffness. Okay, so our clinical relevance, which we are, again, still trying to figure out exactly what our relevance was from, since we got different results than we first supposed. So the findings of the study are significant for advancing research with 3D printed feet by providing data on how different infill percentages affect forefoot stiffness. Clinicians can better anticipate performance when printing Macy feet Within our research, the 60% infill was comparable in performance to the Reese foot, but was not equal in stiffness. Therefore, the propulsive force in the Macy foot is lower. Patients may be able to be taking shorter steps, or also having increased fatigue and energy expenditure in that Macy foot. So this data enables clinicians to make informed clinical decisions backed by research to better meet patient needs and optimize performance of the 3D printed prosthetic.
Some limitations that our study had was obviously our stiffness testing machine. That's the main one. We didn't have the ISO standard machine, but we had our own one that has been made for and customized for our research. Also, a small sample size. We only printed one of each Macy feet, and so there's limitations in printing variations and maybe lattice due to unexpected variations in the percent infill. So just that unexpected result we had. Don't know if that was maybe a 3D printing error or something like that. We're assuming that we can generalize it, but so that's a limitation for our research. And then also a time limitation in that we were testing the instantaneous stiffness of like a freshly printed prosthetic foot. And so if you've been walking on it for a mile or 2 months, you might have a different instantaneous result.
So going into future research, I mean, what's next after everything that we found and we've discovered so far? We still have really a lot of unanswered questions about what this foot is capable of doing. So one of the things that we want to look for in the future is that the way that we tested this foot was not in a cyclic manner. So as Sarah was mentioning, we just got the instantaneous measurement from it. But if we tested this foot in a manner that we saw how many cycles it could go through before we saw it go through plastic deformation or permanent deformation, that could let us know how long this foot could last, its lifespan and longevity, excuse me. And so that's really important because we want to know if this foot is great for patients. Well, that's great, but I mean, if it's going to last 3 weeks, a month, 2 months, is it really worth getting this one versus getting a commercially available one? So that's a question that'll be fantastic to look into. Also, our research only focused on the forefoot, so that kind of ball of the foot area, and we didn't look at the heel at all. As you saw passing it around, that heel is also compressible, and so look into that as well and how it relates to a different part of the gait cycle, right? Because we're looking at toe off, and so we're looking at the heel. We want to know how we can also test how it looks when you're first planting that foot in the ground, right? When you're first loading onto it, how it responds. That's another great area of research. And so, and additionally, we want to be able to look at what other different materials besides this one. Maybe TPU isn't the best, maybe it is. That's not something that we've done in our research, but there's a lot of room where we can grow and see what else we can do with it.
So thank you. Special acknowledgements and thank yous to our principal investigator, David Wilson, who is an adjunct professor at UT, teaches us a lot about orthotics particularly, but really both prosthetics and orthotics. And then Tewo Akinsanya for just being the inventor of the Macy foot and also giving us advice on how to print it and communicating with us that way. And also Amber Johnson from here, LeTourneau University, the Director of Engineering Outreach. Just thank you for her for letting us use her printer and being there for us to help problem solve. And also thanks to Dr. Lowe and all the Maker Lab techs who helped me out when I was trying to figure stuff out. So thank you guys.
Some time for questions for our speaker here. Let's go to lunch. Any questions out there?
Yeah.
Based off of your research right now and other research that's out there, what would be the average lifespan?
Of a foot,
This,
we have no idea. Because you can't compare. We don't have any data on cyclic testing and fatigue strength because we were only focused on that proof and ultimate strength, but lifetime directly relates to fatigue strength. So we would have to go under like cyclic loading for like 10,000 cycles. But in general, you want your foot, warranties are typically about 5 years. So you want to at least that could be good.
And he invented this last year. So my assumption, yeah, it's pretty recent, so there's nobody who's been wearing it for that long yet, so.
I would say for me, I'm interested in like research and design, but my ultimate focus is patient care. So to do prosthetics orthotics is a research requirement, which is technically why we're all doing this. I do have a background in research, and some of us have interest in getting PhDs and going on to do design work. But if you want to be like a CPO, prosthetist orthotist, the closest I think to where you can still have patient care is being like a trusted clinician that one of those big companies would reach out to, and you could give your feedback to them. Unless you fully dive into that research PhD setting, then you could do some more design and research. But I think what brought all of us to the field was patient care.
And there's a ton of holes in research in prosthetics and orthotics, like a huge gap. So it definitely needs to be filled if anybody's interested in doing that, for sure.
So you got a lot of critique. It's from
Table.
Table. Do you have a recommendation for input? How did you kind of what variables to make?
Yeah, so he gave us a range of what they had been printing. So he's been very generous in working with lots of different people to get research and information, because his main goal is to make this foot accessible. And so he gave us recommendations for a range. And so that's kind of why we chose different infill percentages, just kind of get an idea, a starting place, because there really isn't a ton of research on that. So yeah.
Kind of interested in this gyroid structure that you chose to kind of give flexibility, and yet it allows for weight. Is this similar to like the bones of birds? Because I know birds have bone structures that have sort of air gaps in it to make it lighter weight. Is this similar to bones of birds?
Well, it's like with ossification, now there's always little holes in it. I don't know if there's any methodology for how those holes are like formed, or I don't know if there's any repeatable patterns. Interesting thing to look into. But yeah, I think it would relate to somehow the holes provide flexibility, but also rigidity.
So this is for K1.
K2.
And so K2 is normal. What is the K2 category?
Think of like your grandma or grandpa who just like goes in and out of the house, maybe goes to the grocery store, but they're not walking faster than.
Is there any reason that this is created for that kind of population? So K2, specifically K2 focused?
The reason for that being is because you have one selected walking speed. That is really what differentiates K2 from K3. So your K3 is just like your average Joe. You can walk in the grocery store. Oh, you see, oh, I got to speed up to cross the crosswalk. Whereas your K2, you're just walking at that one speed, so you don't need as much energy return or propulsion. And you're not putting a ton of force to get out some of that energy that you would need.
So how they determine K2 or K3, they have to use certain prosthetic. They are wearing certain.
It's kind of like you can put K2, K3 components. You can put a K2 component on a K3 patient or a K3 component on a K4 patient, but you can't go down. So you can't put a K3 component.
For insurance purposes.
Yeah.
Evil insurance.
How would you do it inside this? With the 3D model scale differently.
Yeah, so it can absolutely be scaled differently. And then also, I just passed around, there's a lot of ridges. You can reduce the number of ridges. right? So when you scale it down, you can reduce the number of ridges and you can make it, we've seen on LinkedIn, they print like pediatric feet and like really like this big, like they're tiny little things, but you basically, yeah, you scale it down. I think you use the same infill pattern, but you can vary, again, you can vary everything in size and shape, but also the main part is that these ridges are going to be reduced. The number of ridges is going to.
We also just requested the 24 centimeter foot, so you could just request the 27. So it's, yeah.
Thinking about doing research with
It's a great question. It's tempting too, just because like it's really cool, right? Like the Paralympians, right, are all K4 patients or all K4 people, so their activity is super high. It's super great to see them. Again, kind of like as Laura mentioned, really, well, we are healthcare providers. I think most and foremost, that's why we got into the field. I think research is fantastic. We need to develop the field for sure, and we need to create newer, better things for a patient. But it's particularly in our degree, what we're here to do is not so focused on developing it in that way. We're focusing on taking care of patients. So we provide the healthcare for those kinds of patients, and that's the main focus of our education, and pretty much in the reason we got into the field. So definitely necessary, but I don't think it's specifically our motive.
Yeah, and also to tack on to that, I don't think 3D printing has come up to a way where we can have like some of these carbon fiber structural materials that can give you some energy return that you would need for a K3, K4 foot. Yes, engineering and 3D printing has advanced, but not enough in the healthcare space to provide those materials to where we could easily do some benchtop testing. So that's where you would have to reach out to like OSER, Autobox, some of those bigger companies who are actively making those feet with that carbon fiber and other fiberglass carbon fiber materials to do research with those. That would be very non-costly. Expensive.
Well, I think we've run out of time, but if you have more questions, please come down with Ronnie and visit with our speakers. Also, if you have more longer questions, please join us in the Joyce Room on the cafe. If you don't have a meal plan, we can take care of you there. So let's thank our speakers one more time. Okay, well, okay. You were there. Yeah.